Infrared spectroscopy. So this is an introduction to infrared spectroscopy where I'm just going to introduce you to the technique, how it works and why it works, and just some basic AS molecules that we'll have a look at how they are analysed and what they look like in terms of the spectra. So infrared spectroscopy is a technique that chemists use to give some information about the type of molecule that they're analysing. So basically the functional group that the molecule contains. So for example, it might be that the functional group could be an aldehyde or a ketone, or maybe an alcohol or a carboxylic acid. Now how does it distinguish between these different groups? So each molecule contains different atoms connected by bonds, and these bonds are constantly vibrating at a particular frequency. And now that frequency depends on many factors, the atoms involved and the length of the bonds and so on. But the key thing is that the frequency that this is occurring at is quite specific to that particular functional group. So for example, if we look at the molecule of water, something quite simple, you might get a symmetric stretch, or you might get an asymmetric stretch where you have one atom of hydrogen moving in and one moving out, or you might get the actual molecule bending. Sometimes people call that wagging. Now how does that actually give rise to the spectra that you will see? So each bond is actually vibrating at its own unique frequency, and that depends on, as I've said, it could be the bond strength, the length of the bond, the mass of each atom at each end of the bond, what they are. But whatever those bonds are, we're talking about organic molecules, so they are all going to be pretty much in the infrared region of the spectra, of the electromagnetic spectrum. So what does the infrared spectrometer do? So here's a diagram of the infrared spectrometer. So you have a source of electromagnetic radiation, and that is passed through your sample, which is in a tube. But at the same time, there's also a reference beam going through a reference. Now, the infrared, some of this infrared will be actually absorbed by the sample. And so some of that frequency will then not pass through the actual sample, and so it isn't in the transmitted beam, which is going to be analysed. Now that's done for a variety of frequencies. So you would start at the low end and you would build up and get a different incident ray going through your sample at a different frequency until you'd gone through the whole infrared spectrum. So each bond will be actually vibrating at a specific frequency, and if that infrared is in the similar range to that frequency, it will be absorbed by that bond, and that bond will absorb it and therefore remove it from the infrared that's coming into the sample, and therefore it will be omitted, if you like, from what's coming through onto the recorder at the other end. And then that is compared to the reference sample to actually give rise to a plot. So how does that work in practice? So you'll have a range of infrared frequencies and you'll shine those through your sample one at a time, and you will find out which frequencies have been absorbed by your particular compound. Now how much of that infrared radiation is getting through can be measured by something called transmittance. How much of the infrared has been transmitted through the sample. So that is called the percentage transmittance. So for example, if 100% of the infrared radiation was transmitted, i.e. none of it had been absorbed by the actual compound, you would see that on the plot 100%. Obviously if you only had a 5% transmittance, then nearly all of the infrared radiation at that particular frequency would be absorbed by the compound, and it's a very high absorption, and that will tell you what bond is present in the compound, because it is a high absorption of that particular type of radiation. Here's a spectra, so you can see there's a series of what you would look at and say there were troughs because they're pointing downwards, but actually infrared spectrums are referred to as having peaks. So how do we interpret this? So it will be set on a axis, as I've put up. So you can see this is the transmittance over here on the y-axis, and obviously 100% transmittance means all the infrared has gone through the sample, none of it's been absorbed. 0% would be all of the infrared has passed, as none of it's passed through the material, it's all been absorbed. And therefore on this side of the spectrum you can see absorbance, and you can see it's exactly opposite, so 100% absorbed or none absorbed. Along the x-axis you can see we have frequency, the frequency of infrared radiation passing through. Now it has a bit of a strange unit, something you won't have seen before, wave numbers, and you're just going to have to accept that that's although you would normally think of frequency as being in centimetres to the -1 or hertz, we're going to call it wave numbers in centimetres to the -1. The key thing being that you can read the numbers and where the peaks are falling. So we have a peak here that's 1740, something like that, and that's obviously an important peak because it's highly absorbed the infrared at this point. So this is going to be quite an indicator of the type of bond that the molecule may contain. So the vertical axis is going to tell you how much has been absorbed. So the larger the peak, the more it's been absorbed. The horizontal tells you the frequency, so you will be able to read where these peaks are falling and be able to read the specific frequency in wave numbers. This is the word that you're going to have to use in your exam, wave numbers. So we now have seen a general spectra. So why do we use this as chemists? Obviously, first of all, it's going to tell you a particular molecule, what bonds is it going to contain, and with AS we're specifically looking at OH bonds for an alcohol, or maybe in a carboxylic acid, or a carbonyl, a C double bond O. So those are the types of bonds that we're going to be looking at, which will be characteristic at a particular frequency on the spectra. What else can it tell you? Actually, what you can do if you have a computer with a database of infrared spectra, you can directly identify the molecule that you have, because you can compare it to known spectra and overlay it, and if it's exactly identical, the fingerprint region of the spectra is identical, which I'm about to show you, then you will be able to say for sure, definitely this is the molecule that I have present. Now where's the fingerprint region? It's actually at the low end of the frequency here, so up to about 1400, maybe up to 1450, down to probably about 600 or 700, something down this end. Now these actual peaks that we can see here don't identify the functional group, but what they do have are peaks very specific to the carbon-carbon bonds, the carbon-hydrogen bonds, and because all organic molecules have these, in terms of can you identify the molecule, no you can't. You can't say it's an alcohol, you can't say it's a carboxylic acid, but you can say yes, it's an organic molecule. However, this is a fingerprint because certain molecules will have a very distinct pattern here in their CC and CH area that you can overlay with a known spectra and know for sure you have. In terms of your exam, no, you won't be able to use this, and do not quote any peaks in this region because they're not going to be useful in terms of identifying, because the majority of organic molecules will have peaks in exactly the same areas So therefore it's not going to be an identifier. What's much more interesting are the peaks at this end, because they are specific to alcohols, carboxylic acids, aldehydes and ketones, which are the molecules that we have studied and the molecules that we're interested in. So you've got your spectra, you've looked at the peaks, you've ignored the fingerprint region because you're not able to analyse that. So what molecules are you expected to be able to analyse? So the first one is an infrared of a carbonyl. So carbonyls, the specific frequency we're looking at, which is around 1700 here, shows a very distinct sharp peak in that region. And carbonyls are either aldehyde or ketone, the C double bond O peak basically. And if you see a peak in this region, then you know you definitely have a C double bond O. Remember, in the exam you'll be given all of the data with the numbers specific to types of bonds. You don't have to learn these actual wave frequencies, but you need to be able to identify them once given those in the exam. So that's one particular molecule you're going to have to analyse. Second one is an alcohol. Now the alcohol is distinctive, much higher in frequency, and you can see it's a much broader peak. It's not as sharp as the carbonyl peak. So there you've got a peak between 3200 3600. It's broader, it's on its own up here, so you can identify, yes, again you've got this fingerprint region that's not going to be specific to tell you any information about what molecule you've got, but here we've got this very distinctive OH broad peak. The third type that you're going to have to analyse is a carboxylic acid. Now carboxylic acid, as you know, has got a C double bond O and it's got an OH, so it's got both peaks forming at the same time, but one quite distinct difference that you need to be aware of. So you have got a much broader OH peak than before, but you've still got the nice sharp C double bond O. So it's a much broader, and that's because you've got hydrogen bonding, which interferes. So these are the three that we've looked at. We've got an OH distinctive peak. You have got an aldehyde, C double bond O, or a ketone. And finally you've got a carboxylic acid where you have both, but the OH is much broader than it would be in an alcohol. So what should you be able to do? You need to understand where the infrared spectra have come from, the fact that bonds are vibrating at a particular frequency and they may well then absorb infrared radiation at the same frequency when exposed to it. It can identify particular functional groups such as alcohols, the OH, carbonyls, C double bond O, and you need to be able to contrast the three specific spectra of alcohols, carbonyls and carboxylic acids. Can you do those? Can you do all three of those? Yes or no? Come to the lesson and we are going to be looking at lots of spectra and being able to identify them, but hopefully with this you're going to be able to get going a lot faster.